This lesson deals with supplemental problem 2.6. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems, starting on page 10. This supplemental problem takes a look at what are called log and anti-log amplifiers. There's two shown down here. First one's called a log amplifier. I'd like you to find an expression for the output in terms of the input, and under what conditions would these expressions be valid. And likewise, here's an anti-log amplifier. You can see that the diode and the resistor get changed, and also the direction gets changed. And again, can you find the output in terms of the input, and under what conditions would these equations be valid? Take a look first at the log amplifier, where we have a diode in the feedback loop of the op-amp. And we know that for the diode, that the current is equal to the value of I sub s times the quantity e to the v sub d over a to v sub t minus 1. And if we're strongly forward biased, we can throw the 1 away. And of course, we could also solve for v sub d. Take the ratio of id to I sub s, take the natural log of both sides of the equation, and cross multiply by a to v sub t. Assume this is an ideal op-amp. First step is no voltage, no current. There's no voltage here, then the voltage v sub s is across the resistor. That will result in a current, v sub s over R1, and that will become the diode current. And then our output voltage is going around the loop. The rise in voltage would equal the drops, which would be minus v sub d plus 0. We have that v out is equal to minus v sub d. We can grab this equation. A to v sub t, natural log of I sub d over I sub s, but I sub d is equal to v sub s over R1. Now you can't take the log of a negative number. You will need the v sub s to be greater than 0. I have an output voltage that's dependent on the value of the input voltage and the natural log of it. This type of circuit is used to prevent saturation of the amplifier. You can only get so much voltage out here because of the power supplies. And what this is going to do is compress the signal. These are mostly used to detect the signal's strength, but not a specific value of it. Just one application. Take a look at the anti-log amplifier. We'll assume this is an ideal op-amp. The voltage across the input terminals is 0, and the current entering the plus and leaving the minus is also equal to 0. We have a current in the diode, and that's the same as the current that's in the resistor R1 because there's no current here. If you go around the loop, the rise in voltage is Vn, the drop is equal to minus v sub d plus 0. Vn is equal to minus v sub d. Again, our Shockley equation is that I sub d is equal to I sub s times the quantity of e to the v sub d over a to v sub t minus 1. In this case, v sub d is equal to minus Vn. If we're strongly forward biased, we can throw away the 1. We can approximate I sub d as just this expression. Then we could solve for V out. Go around the loop here. The rise in voltage is equal to the drops. The rise in voltage is V out. The drop is I sub d times R1 plus 0. V out is equal to I sub d times R1. Here's our expression for I sub d. Multiply that by R1. And I now have an expression for V out. If Vn is positive, this is an extremely small number. It'd be hard to detect. So let's assume that Vn is actually less than 0. That would make this a fairly large number. Typical application for this is to take the log circuit and compress the signal, then to transmit it, and then to receive it, and then to uncompress it. If I were to substitute in this for Vn, I would get the two minus signs canceling. The a to v sub t's would cancel. And I'd have e raised to the natural log of v sub s divided by R1 I sub s. E raised to the natural log is just the argument. The R1 I sub s would cancel with this, and we get that V out equals v sub s, the original signal. And this is supplemental problem 2.6.